So far we have been working with plane waves. That is one of the solutions of Maxwell's equation. Today we are going to ask the question, can we come up with a procedure to write different types of solutions? That is achieved via what's known as auxiliary vector potentials. Yeah, let us consider the Maxwell's equations. I don't think I need to give any commentary on this. The two divergence equations can be written in terms of del dot H and del dot E. Sometimes we use del dot B, sometimes we use del dot H. Similarly with del dot E and del dot E. Now let's take the curl equation curl of E and take curl of E, which is minus del cross M minus j omega mu del cross H. Now we know that curl of vector is gradient of divergence of the vector minus del square of the vector. This is a vector identity. Please remember that. Now del dot E is given by QEV upon epsilon. So we are going to substitute that here. And del cross H is given by J plus J omega epsilon E. That we are going to substitute here. Let me pull out the pointer so we can see that. So del cross H is being replaced by J plus J omega epsilon E, and del dot E is being replaced by QEV upon epsilon. So we can write this as del square E plus omega square mu epsilon E is J omega mu J. We're going to move it to the other side. Then we have del cross M, move it to the other side, plus 1 upon epsilon del QEV. We are allowed to do this if we are considering homogeneous medium. That means epsilon is not a function of position. Therefore, it is a constant as far as the space is concerned. Similarly, you can derive an equation in terms of H. Ideally, if I want to find the fields, I'm supposed to solve this equation. It looks very complicated because I know J, I know M, but to get E out of that is very tough. People have made attempts. Yeah, it's possible to solve it. It's very intense and complicated. Therefore, we will find a slightly different approach. Little more systematic, a little easier to handle in terms of the mathematics that is associated with it. So let's talk about what's known as vector potential. Consider a region where M is 0 and QMV is 0. That means there are no magnetic sources. Then the Maxwell's equation will reduce to this form here. We got rid of M from here and we got rid of QMV from here. Now we know identity, and we know an identity, divergence of curl is always 0. Since we know that del dot B is 0, we can represent B as curl of some other vector. And we call that vector as vector potential A or magnetic vector potential A. So BA, we are going to now make a distinction between the fields due to A and fields due to something else. We'll come to that something else in a moment. So we have put a subscript here. A indicates that this B is due to the vector potential A. Okay. Therefore, HA is 1 upon mu del cross A. Quite straightforward. Now what do? We will go to the next Maxwell's equation, or the curl equation. Del cross EA is from here minus j omega HA, and HA is known, therefore it is 1 j minus j omega del cross A bar. Okay, we can combine these two. Yes, we can write del cross of E plus j omega A is 0. We just have to go to the left hand side, dot the del cross outside, very straightforward. We know one more vector identity. Curl of gradient is always 0. Therefore, you can express this quantity as gradient of a scalar, which is del phi E. Phi E is the scalar. We have put a negative sign for consistency. A positive sign would have worked very well as well. So EA plus j omega A is minus del phi E. Therefore, EA can be written in terms of A and phi E. What's the meaning of this? If I were to know the vectors A and scalar phi E, in terms of A and phi E, I can write the solutions of the Maxwell's equation HA and EA. Good. Still, I don't know how to find A and phi E. We are going to figure that out in the next slide. We have defined the vector potential A as BA is equal to del cross A. Take the curl on both the sides and expand del cross A as del dot A minus del square A. Now take one of the Maxwell's curl equation, the Ampere's law, and substitute for del cross H in this equation here. And what we have is a result which is given here, mu times j plus j omega epsilon EA is given equal to del dot A minus del square A. Now we know the relationship or equation to E as well in terms of A and phi del phi, and substitute here in this equation and expand this term here, and what we have is mu j plus omega square mu epsilon, this quantity here, minus j omega mu epsilon del phi E equal to del dot A minus del square A. Do you realize what we are trying to do? Not yet. This is the most important step, the next step. We choose del dot A equal to minus j omega mu epsilon phi. There is a result called Helmholtz theorem. If we define the curl of a vector and divergence of a vector, then the vector is uniquely defined. We'll pause the proof of this theorem for the moment. So what we take from the essence of that is, if you have a system, you can define the curl of a vector and divergence of the vector independently. You have the choice. You could have chosen any definition for del dot A. By choosing del dot A equal to minus j omega mu epsilon phi E, what we are achieving is these two terms will get cancelled. And we have a nice result for A in terms of J. Look at the beautiful part of this. If you know J, you can calculate A by solving this differential equation. We still don't know how to do it, but what we know is the direction of A and direction of J will remain the same. That's a very powerful reduction that we have achieved, simplification that we have achieved. In the earlier problem, when you are trying to solve E and H from J or M, direction of E and H were not related to J or M in a straightforward manner. Whereas in this equation, direction of A and J are the same, which is very helpful and handy. Now, given A, that is given, if I can find a solution to this wave equation, this is called inhomogeneous wave equation. For A, I can find out HA via this result 1 upon mu del cross A, and I can also find out E by this quantity here, because I have substituted for phi from this equation del dot A upon minus j omega mu epsilon over here. So given a system, if I can find out A, I can find out HA, I can also find out EA. There is another way to find EA. In case there are problems where we have a source confined to a finite region and you are trying to find the fields far away from the source, and if you are interested in the fields far away from the source where j is 0, you can use this result to compute the value of EA. That's what is done in antenna problems. So we can now think of vector potential, another vector potential called vector potential F. Let us consider a situation where J equal to 0 and QEV equal to 0. Then the Maxwell's equation will reduce to this form here. I'm going to go a little faster here, but what I suggest to you is pause the video, work out all the details. Once again, divergence of curl is 0. Therefore, from this del dot D equal to 0, I can write define vector potential F. Okay. Once I define vector potential F, I can compute E in terms of F as minus 1 by epsilon del cross F. What's the next step we are going to be doing? Yes, we are going to take del cross of H equal to minus j omega epsilon EF and substitute the value of E from here. And we take this term to the left hand side and define a potential scalar potential phi as the gradient of phi will be equal to this quantity here, and that phi we call it as phi m. Okay, and hf therefore is expressed in terms of f and phi m via this equation here, very similar to what we did with a and phi e. So here we are expressing the fields in terms of vector potential f and scalar potential phi m. So what is the next step? The next step is we want to write a differential equation in terms of f so that we can. How do we do that? We start with our definition of f and we take the curl of this quantity here and we use the Maxwell's equation, the Faraday's law in this equation here, and expand or use the equation for hf in terms of f and phi m in this equation where here, and expand this term here, and what we have is an equation in terms of both f and phi m. We still haven't defined the divergence of f, therefore we define the divergence of f as minus j omega mu epsilon phi m, and in that process this will get cancelled off, and what we are left with is a inhomogeneous vector wave equation for evaluating f in terms of the magnetic current m, very similar to the equation for A. And therefore, once we solve this equation, find the value of F, you can evaluate the electric and magnetic fields due to F via these results. When you have both electric and magnetic sources, we can compute HA, EA, and EF, HF in terms of A and F, and the total field will be sum of these two electric fields. E is EA plus EF and H is HA plus HF. I don't even want to recite this long equation, and I don't even expect you to remember this long equation, but I would like you to know that such a result exists. Now, where A and F are the solutions of the inhomogeneous vector wave equations shown here. When we are talking about radiation problems, especially far away from the antenna, the first step will be to solve the differential equation, the vector wave equations given here, find out A and F depending on the nature of the problem, and compute HA, and of course del cross H is J plus J omega epsilon E. We know that. If you are trying to find out the field away from the antenna, J will be 0 there. Therefore, you can take curl of this and compute the electric field. That's quite straightforward. Similarly, if I want to find out the field due to this magnetic current M, I approach the problem via the vector potential F. We solve this del square F plus omega square mu epsilon F equal to minus epsilon M bar. And once we get the value of our equation for F, we compute the curl of F to get the electric field. And we know that in the source free region, M is 0. Therefore, we can compute H as 1 minus 1 upon j omega mu del cross EF. This is valid if you are trying to find the fields of an antenna where the sources are confined to a small volume and the fields are getting evaluated away from the sources. And of course, the total electric field and magnetic field will be sum of these respective components of electric and magnetic fields. It looks a little odd today because what I'm trying to show here is certain equations, certain results which do not have any significance at all. We don't even know what is J, we don't know anything about M, we don't know how to solve this wave equation. I mean, so many unknowns are hanging around here. I hope as we go along, by the time we come to the end of this course, you'll be able to have complete familiarity and command over this whole process of the solution, whole process of finding the fields given sources via the vector potential approach.